Please open Guidelines for Evaluating Integrals involving sine and cosine. We're going to talk now about how you get antiderivatives of trigonometric integrals. And trigonometric integrals are integrals involving powers of trig functions. We're going to start by looking at integrals involving powers of sines and cosines. If you look at your guidelines for evaluating integrals involving sine and cosine, it's broken up into three steps. Let's take a look at an example of the first step. The first case has a sine raised to an odd power, like sine cubed theta, and a cosine. Let's say cosine to the fourth theta. Now in this case, what we're going to do, we look for the sine or cosine that's raised to an odd power, which is that sine cubed, and we're going to take one of those sines and put it back next to the d theta. And what we're doing when we do this is preparing for a substitution. So that leaves us with just a sine squared theta, cosine to the fourth theta, and here's that extra sine theta. Now this thing here is going to turn out to be our dw, or possibly our negative dw. So if the sine of theta is the derivative of our substitution, what is w going to be? Well, it's going to be the cosine of theta. Well, if w is a cosine of theta, then over here all I want to see is cosines. But this is a sine squared. How do I get rid of that sine squared and turn it into cosines? Well, I use that Pythagorean identity that says sine squared theta plus cosine squared theta equals 1. And if you solve that for sine squared theta, you get sine squared theta is 1 minus cosine squared theta. And we get this integral. Now we're ready to do our substitution. W is going to be cosine of theta, and dw is going to be the negative sine theta d theta. Now let's just multiply both sides of this equation by negative 1. So we get negative 1 dw equals sine theta d theta. Okay, now we can go ahead with our substitution. This 1 minus cosine squared becomes 1 minus w squared. Cosine to the fourth becomes w to the fourth. The sine theta d theta becomes negative 1 d theta. And if you distribute that negative 1 and the w to the fourth through this parentheses, you're going to get w to the sixth minus w to the fourth dw. Whoops. This is a dw, not d theta. Did everybody follow how I did that? Okay, then getting the antiderivative, this is pretty easy. It's going to be 1/7 w to the 7th minus 1/5 w to the 5th. And if we replace w's with cosine of theta, we get 1/7 cosine to the 7th theta minus 1/5 cosine to the 5th theta plus c. And there's our antiderivative. Now let's go on to case 2. In case 2, we have cosine being raised to an odd power, and we don't really care what power the sine is raised to. So let's take a look at this integral. Sine squared theta times cosine to the 5th theta d theta. So here the cosine is raised to an odd power. And what we're going to do here is pull one of those cosines off and stick it with the d theta. That leaves me with a cosine to the 4th theta. And here's that extra cosine. So this cosine theta d theta, that's going to be the derivative of my substitution. That's the derivative of w. So what is w going to be? What trig function has a derivative of cosine of theta? Well, it's sine theta, right? So I want everything over here to be in terms of sine thetas. But this is a cosine to the 4th. Well, just like in the previous example, I can change that into sines by using that Pythagorean identity. First, I'm going to rewrite that cosine to the 4th as cosine squared theta squared. And then I can rewrite this cosine squared theta using that Pythagorean identity. It's 1 minus sine squared theta. And that's squared. And we've got this cosine theta d theta out here. Okay, now we're ready to do our substitution. I'm going to let w be the sine of theta. dw is cosine theta d theta. And right there you can see our dw. So this integral becomes w squared times 1 minus w squared squared dw. And I'm going to use FOIL to multiply that out. So we get w squared times 1 minus 2w squared plus w to the 4th. And then distribute this w squared through that parentheses. And I get w squared minus 2w to the 4th plus w to the 6th. And now we just use the reverse power rule to get the antiderivatives. And we get 1/3 w cubed minus 2/5 w to the 5th plus 1/7 w to the 7th. And then we replace all of our w's with the sine of theta. So we get 1/3 sine cubed theta minus 2/5 sine to the 5th theta plus 1/7 sine to the 7th theta plus c. And we're done. Okay, let's look at the third case. In the third case, we answer the question, what do you do if neither sine or cosine is raised to an odd power? And that's where we have to use these two formulas. These are called reduction formulas because they take a sine squared or a cosine squared and they convert it into a cosine to the first power, which is easier to work with. Now, I want to point something out here before we get into an example. What this formula does, for example, in sine squared, it's taking that angle, theta, and changing it into a 2 theta. So, if we were to take the sine squared of, say, 3 theta, and want to get rid of that square on the sine, we could use this reduction formula to say that's 1/2 of 1 minus the cosine of 6 theta. Because what this formula is doing is it's taking this angle and doubling it to get that angle. So just keep that in mind. So if we had sine squared of 2 theta, and we wanted to apply this reduction formula to it, we would take that angle of 2 theta and double it over here on the right and get 1 minus the cosine of 4 theta. Now let's get to an example. Okay, let's take a look at this example. We want to get the antiderivative of sine squared theta times cosine squared theta. And neither of those is raised to an odd power. So we're going to replace both the sine squared theta and the cosine squared theta using those reduction formulas. So the sine squared theta gets replaced with 1/2 times 1 minus cosine, not cosine squared, just cosine of 2 theta. And the cosine squared theta gets replaced with 1/2 times 1 plus the cosine of 2 theta. Okay, we can simplify this integral by multiplying the 1/2 times 1/2 and pulling that out of the integral, and then using FOIL to multiply 1 minus cosine 2 theta with 1 plus cosine 2 theta. And you notice that's kind of like a difference of squares. So when we multiply that out, we're going to get 1 minus cosine squared of 2 theta. But now we have a cosine squared of 2 theta. So we're going to have to use that reduction formula for cosine squared, which makes that cosine squared of 2 theta into 1/2 times 1 plus the cosine of 4 theta. Remember, we talked about this just a few minutes ago. This angle of 2 theta right there is going to double into a 4 theta. And then we're just going to simplify. We're going to distribute that 1/2 through that parentheses. So we get 1 minus 1/2 minus 1/2 cosine of 4 theta. And we can combine the 1 minus 1/2. And we get this. 1/2 minus 1/2 cosine of 4 theta. Okay, now we can take the antiderivative. The antiderivative of this 1/2 is 1/2 theta. And the antiderivative of 1/2 cosine of 4 theta is going to be 1/8 sine of 4 theta. And if you want to distribute that 1/4 on the outside, you're going to get 1/8 theta minus 1/32 sine of 4 theta plus c, and there's our antiderivative. Okay, now we're going to take a look at the guidelines for evaluating integrals involving secant and tangent. And this is broken down into 5 parts. We're going to concentrate on the first 3 and talk just a little bit about the last 2. Okay, the first case involves integrals that have secant being raised to an even positive power. Okay, so let's take a look at this integral. Secant to the 4th theta times tangent to the 4th theta d theta. So if secant is being raised to the 4th power, or an even power, we're going to pull off a secant squared and put it back next to the d theta. And again, what we're trying to do is set ourselves up for a substitution. This is a very common trick. Whoops, that's nope. Theta d theta. So again, this secant squared is going to be the derivative of our substitution. And if that's the derivative of our substitution, what is w going to be? Well, w is going to be the tangent. So we want everything up here in terms of tangents. How do we convert that secant squared into tangents? Well, again, we fall back on those Pythagorean identities. And secant squared theta is tangent squared theta plus 1. And then it's times tangent to the 4th theta. Then we've got our secant squared theta d theta. And I think we're ready for our substitution. W is going to be tangent theta, and dw is secant squared theta d theta, and right there is the dw. Okay, so tangent squared plus 1 becomes w squared plus 1, then times w to the 4th dw. We distribute the w to the 4th and get w to the 6th plus w to the 4th dw, and get the antiderivative, which is 1/7 w to the 7th plus 1/5 w to the 5th, and we replace w's with tangent theta. So we get 1/7 tangent to the 7th plus 1/5 tangent to the 5th plus c, and that's our antiderivative. Okay, let's go to case 2. Case 2 we use when the powers of the tangent are odd and positive. So here we have a tangent to the third times secant to the fifth. And in case 2, when you have a tangent being raised to an odd power, we're going to pull off one secant and one tangent factor and put it back with the d theta. So this is going to become secant to the fourth times tangent squared times secant theta tangent theta d theta. And again, we're setting ourselves up for substitution. That secant theta times tangent theta is going to be the derivative of our substitution. So what is w going to be? Well, w is going to be the secant of theta, right? Because the derivative of the secant is secant times tangent. So we want everything up here to be in terms of secants. But we've got that tangent squared. We're going to get rid of that tangent squared by using that Pythagorean identity again. Tangent squared is going to be secant squared theta minus 1. Then we've got this secant theta tangent theta d theta. Now we're ready for our substitution. W is going to be secant theta, and dw is going to be secant theta times tangent theta d theta. So we make our substitution. This is going to become secant to the w to the fourth times w squared minus 1, and all of this is dw. Then we distribute this w to the fourth, and we get w to the sixth minus w to the fourth, and integrate, and get 1/7 w to the 7th minus 1/5 w to the 5th, and then we replace our w's with secant theta. So we get 1/7 secant to the 7th minus 1/5 secant to the 5th. And we're done. Okay, let's move on to case 3. Case 3 is no secant factors and tangents being raised to an even power. So let's look at this integral. Tangent to the fourth theta. So in case 3, we're going to pull off a tangent squared. So we got tangent squared times tangent squared d theta. And we're going to rewrite this tangent squared using that Pythagorean identity. So it's going to be, let's see if I can fit it in here, secant squared theta minus 1. And then I'm going to distribute this tangent squared through that parentheses. So I get tangent squared theta times secant squared theta minus tangent squared theta. And then I'm going to break this up into two integrals. Tangent squared theta, secant squared theta, d theta, minus the integral of tangent squared theta, d theta. Okay, let's work on this first integral. And I'm going to have to slide this down. tangent squared theta, secant squared theta, d theta. Well, this is a simple substitution integral. I'm going to let w be tangent theta. dw is going to be secant squared theta, d theta. So then this integral just becomes w squared dw, which is 1/3 w cubed. And I replace w with tangent. So we get 1/3 tangent cubed theta. Okay, so that first integral becomes 1/3 tangent cubed theta minus this second integral, tangent squared theta. Well, let's go down here and draw a little dividing line and work on that. The integral of tangent squared theta. Well, I'm going to rewrite tangent squared using that Pythagorean identity again. Tangent squared theta is going to be secant squared theta minus 1. And this is easy. Antiderivative of secant squared theta is tangent theta minus the antiderivative of 1 is theta. So we go back up here and replace that integral with tangent theta minus theta. And then I distribute this negative sign through the parentheses and I get 1/3 tangent cubed theta minus the tangent of theta plus c. And I'm finished. That's our antiderivative. Okay, case 4. We're not going to go into a lot of detail on this. Mainly, I just wanted to give you this antiderivative. The antiderivative for the secant of theta is natural log of secant theta plus tangent theta plus c. And the antiderivative of the cosecant of theta is the negative natural log of the cosecant of theta plus the cotangent of theta. And if you want to see why these are the antiderivatives, just take the derivatives of these things and you'll see you get back to the secant theta and cosecant theta. Now it would be a good exercise for you guys to find the antiderivative of the cosecant cubed of theta. This would be a good exercise. It's an integration by parts problem. You have to choose u and dv carefully, and it's going to turn out to be a circular integral. So it should be interesting. Give it a try. As for case 5, case 5 is what you do if nothing else works. And what they say in case 5 is convert everything into sines and cosines and just pray that that helps. Okay, that's it.